In this video I show how the combinational logic for my 16-bit computer clock works, and I also show how I built this PCB and prototyped it. So if you want to see all that, keep watching. Okay, so this is a schematic for the combinational logic that I'm going to be using in the clock, and so I'm going to run over what makes it up. So you got the input A, and that's the A stable 555 timer circuit. Got the input B, that's a monostable 555 timer circuit. You got the input C, that's a bistable 555 timer circuit, and then you got this D, which is going to be a halt. And there's 7 NAND gates, and I've labeled them gate 1, gate 2, gate 3, gate 4, gate 5, gate 6, gate 7, and they're all NAND. And if you don't know how a NAND gate works, this is a truth table. So you got 2 inputs A and B, which aren't related to these inputs, it's just what the inputs names are, and then you got an output Z, which isn't related to this either. So in every situation except one, the output's going to be 1. The only situation where it's 0 is when they're both 1, when both inputs are 1. So that's how it works. So now I'm going to give a few examples to explain how this circuit's going to work. So let's say that A is going to be 1, B is going to be 0, C is going to be 0, and D is going to be 0. So let's look at what's going to happen. You have a 1 going to the input of gate 1, and the other input to gate 1 is the output of gate 3, and the input to gate 3 is C, and both inputs of gate 3 is just tied to C. So C is going to be 0, so that means both inputs of this gate 3 is going to be 0, and if we look at our truth table, that's going to result in a 1, so you're going to have a 1 here. Now you have 2 1s going into gate 1, and that's going to result in a 0, so you have a 0 here, and that's going to go into gate 4. The other input to gate 4 is the output of gate 2. Let's look at what we have in gate 2. In gate 2 we have 2 zeros from inputs B and C, so the output you're going to get is a 1. And so if we look at our truth table now, we have a 0 and a 1, that's going to result in a 1. So you're going to have a 1 inputted into gate 6, and here you have the same situation as C. So you're going to get a 1 out of here, out of gate 5. So now you have 2 1s here, that's going to result in a 0. Now you have a 0 going into both inputs of gate 7 from gate 6, that's going to result in a 1. And Z's our output, so we're going to get 1 as our output. And you could see now we're going to run through this again, except make A 0 and B 1, and now we're going to make C 1, and we're going to keep D at a 0. So I'm going to go through this a little quicker now. So you have 2 1s going into gate 3, so that's, you're going to get a 0 here, and now you have 2 zeros going into gate 1. Now you're going to have gate 1 outputting a 1 into gate 4. Out of the other input to gate 4 is the output of gate 2. In gate 2 you have a 1 and a 1, 2 1s equal a 0. Now into gate 4 you have a 1 and a 0, so now you're going to have a 1 outputting from gate 4 going into gate 6. Gate 6, its other input is from gate 5, you have a 0 here, so you're going to get a 1 out here. Now you have 2 1s, so you're going to get a 0. Then you're inverting that and you're going to get a 1. Because when you tie both inputs of the gate together, you're basically just inverting it. So if you tie them both together and you put in a 0, you're going to get a 1. And if you put in a 1, you're going to get a 0. So you might have noticed that if C is set to 1, the output is going to be whatever B is. If C is set to 0, you're going to get at the output whatever A is. So if C is our bistable, we can switch between 1 and 0 easily. And then if A is our A stable and B is our monostable, we can basically switch between outputs by using C. So if C is set to 1, we're going to be listening to B. If C is set to 0, we're going to be listening to A. And D is our halt. So what this does, if I set D to 1, you're going to get a 0 here, and then you're going to get a 1 outputting to here, and then you're going to get a 0 here, no matter what gate 4 is doing. So this is basically an override. If we pull this high, no matter what's happening with these, Z's going to be 0, no matter what. So what this does is gives us a way to switch between astable and monostable, and also stop the whole clock if we want to. And so these are the chips I'm going to be using. They're called the CD4011BE, and this is the layout of them. They got 4 NAND gates in them, and I'm going to be using 2 of these chips. So there's one of these NAND gates I'm not going to be using because I'm using 7 NAND gates. But basically this is the layout. You see the inputs A, B, C over here and the hold over here, and I've also added a LED to show us the output, and you can take a look at this if you want. You can take a closer look at it. I don't really think I need to go over it because I already explained how the circuit's going to work, but this is just the layout, so it's there if you want to take a better look at it. Okay, so now I'm going to build this circuit on a breadboard. I've already got the chips in and I've already hooked up power and ground, and I'm going to start up by connecting the astable output to one of the inputs of gate 1. And now I'm going to connect the monostable output to one of the inputs of gate 2, and the bistable output to the other input of gate 2. Now I'm also going to connect the bistable output to one of the inputs of gate 3, and then I'm going to connect both inputs of gate 3 together. And now I'm going to connect the output of gate 3 to the other input of gate 1. And now I'm going to connect the output of gate 1 to one of the inputs of gate 4, and I'll do the same for gate 2. Now I'm going to plug a jumper lead into one of the inputs of gate 5, and this is going to serve as the halt line. And now I'm going to connect both inputs of gate 5 together. Now I'm going to connect the output of gate 5 to one of the inputs of gate 6, and the output for gate 4 to one of the inputs of gate 6. Now I'm going to connect the output of gate 6 to one of the inputs of gate 7, and now I'm going to connect both inputs of gate 7 together. Now I'm going to connect the output of gate 7 to a LED that's connected to a 220 ohm resistor, which then goes to ground. So now I've got Easy EDA open and I'm going to build the circuit. So first I'm going to need the NAND gate chip. I need 2 of them, and I'll turn them around like that and I'll move that to over there. Now I'll connect the output of the astable circuit to one of the inputs of gate 1 and the monostable to one of the inputs of gate 2. Now I'll connect the bistable output to the other input of gate 2, and I also need to connect it up to both of the inputs of gate 3. And I also need to connect up power and ground, I forgot about that. Now I'll connect the output of gate 3 to one of the inputs of gate 1, and now I can connect the outputs of gate 1 and 2 to the inputs of gate 4. Now I'm just going to connect both inputs of gate 5 together. Now I'll connect the output of gate 5 to the input of gate 6, and the output of gate 4 to the other input of gate 6. Now I can connect the output of gate 6 to the inputs of gate 7, and now I can connect an LED to the output of gate 7, and connect a current limiting resistor, and then connect that to ground. So that's all the combinational logic for the clock that we're going to need on Easy EDA. Now I can actually draw the PCB, so I'm going to save that, and now I'm going to create the PCB. I'll get rid of the board outline for now, and so these are all the components lined up. So now I just need to position them nicely and then start mapping it out. Okay, so it's all positioned how I want, so I think I'm ready to start making the connections now. So I'll just go through all the connections and just make them. So now I need to put two pads in the PCB where I can connect power and ground and connect an output. And so now I'll change their nets to what they should be connected to, so this can be power. So I'll do VCC. This can be ground, so I'll do GND. And this can be the output, so now I can connect this. I'll connect VCC to just one of the powers because they're all connected now, and ground can stay like that for the moment. And one last output that I'm going to want to need for purposes much later on in build is an inverted output. So that's going to be easy to do because we have an inverted output here. This isn't what the output should be, but then it's being inverted, and now this is a real output. So if we just use this as the inverted output, that'll work. And now connect it up. Okay, so now we got pads where we can plug in power and ground, and we have an output and an inverted output. Now I want to add in some holes into the PCB so that I can fit M5 screws in to bolt it down to a wooden board or something like that. So I'll put them in 4 corners. And so the dimensions of that is the whole diameter is 5mm and the width is 7.5mm. Okay, so now I have 4 holes and I removed all of the nets off them just so they're not connected to anything, so they have no nets. And now what I'm going to do is I'm going to create a board outline. So I'm going to get my board outline. I'm not doing it to any particular size, I'm just doing it so that it's well enough away from the screw holes. So I got 4 screw holes and a board outline, so now I'm going to add some text. So this one can say 16-bit computer clock module, and I'll write I'm on a bus down here. Now I'll try and get them nice and straight. And one thing I actually forgot to connect was a halt line, so I'm going to connect that now. So all the connections are made except for ground, so I'm going to do a copper region. So I'm going to set the net to ground, and then I'm just going to encircle the whole PCB. So now you can see all the connections are made. Got my writing here, got screw holes. It's looking pretty good, so I think I'm going to order this now. Okay, so the PCB's arrived and this is what it looks like. It looks pretty good. Here's a look at the back of it. So now I'm going to solder this all together and see if it works. Okay, so I've soldered it together and turned it on, and it's not quite working. This LED is always on where it should be only on when I push the button, and now I'm pushing the button and it does nothing. And also these 2 LEDs won't switch between each other. If I push the 2 buttons, nothing happens. it doesn't switch from one LED to the other and the outputs don't switch. And so you might have noticed that the two circuits with buttons hooked up to them aren't working. And this is because in the PCB design I switched the buttons around. Right now they're not the way they should be. So the 555 timer should be hooked up to this pin of the button instead of this pin, and same goes for this button. So instead of only being connected to ground when I pushed the button, it was always connected to ground, so only one was ever going to be set. Same with this. This was always connected to ground, so the LED was always on, because as far as the 555 timer was concerned, I was always pushing the button. I'm just going to change the connections to these buttons. So I'll connect that there, get rid of that, and then I'll do that for the other buttons. Okay, I updated the PCB, so now I'm going to fix it. I'm going to get rid of the copper region first, and now I'm going to make the right connections. Okay, so I fixed all the connections I needed to fix, so now I'm going to do a ground copper region. Okay, so the PCB is done now, and I think I can reorder it now. Hopefully it works this time. Okay, so the PCB is finally arrived. Now I'm going to solder it together. Okay, so now it's all soldered together. It looks pretty promising. Hopefully it works. And so to power the PCB, I've just got power plugged into a breadboard connected to positive and ground leads, and then I'm going to connect that to the PCB. So now the PCB is all connected up and it looks like it's working. I can try and switch to the monostable mode, and it flashes whenever I push the button, so that's good. It seems like the buttons are working, and I can go back to astable mode. So it looks like it's all working. So now I'm going to try and hold the clock, and whenever I plug 5 volts into the halt line, the clock stops, so that's a good sign. And now when I connect the halt line to ground, it does nothing as it should. So now the clock module is fully working, I can start building the next parts of the computer, which is going to be the register. The register is going to be the next part of the computer that I'm going to build, so stay tuned for that. Thanks for watching.